Our fourth session will start with Dr. Mehmet Ali Küçüker from the İzmir Institute of Technology by the speech title of Investigation of Biofilm Structures of Chlorella vulgaris and Ettlia Oleoabundans species on an anti-biofouling coating. The stage is yours.
Hello everyone. It's a really difficult time to be here because of the earthquake, but we are set. However, the professional life is going on, so we are here. I would like to thank the whole organization here. First of all, I would like to show our last results from our project, which was related to investigation of biofilm structures of two different microalgae species on the anti-biofouling coating. So, in the previous presentation, we observed there are main global issues which are listed like this: energy, water, food, and environment. So, nowadays, researchers have focused on solving these problems. We always discuss with Professor Berat Haznederoğlu. He always mentioned that we can find a solution for micro problems using microalgae. We know its great potential. It has a lot of properties to solve this problem, such as the most efficient photosynthesis, high growth rate when we compare the ordinary foods. Independent of agricultural land, it can be grown in fresh, salt, and brackish waters. So it has a potential for carbon dioxide removal. And we utilize microalgae to treat wastewater, and also we can utilize microalgae to remove phosphorus and nitrogen from wastewater as well. Mainly cultivation system depends on the two categories. One of them is open pond system. You can see the right corner of the slides: raceway, pools, and ponds. And there are engineering systems, mainly photobioreactors, glass tubular photobioreactors, panels, flat panel photobioreactors, airlift photobioreactors, and column photobioreactors are mainly used. We mainly focus on the closed system because of the European microalgae cultivation depends on the closed system. Approximately more than 70% of the cultivation systems belongs to closed photobioreactors. So we focus on to increase the efficiency of closed system, mainly tubular systems. That was our project, which was funded by the TÜBİTAK, and we aim to increase the performance of the tubular photobioreactors, and that will allow to produce of reactors with the high light transmissions, and we would like to decrease in biofilm generation on the surface of the bioreactors. And we improve and develop special coating materials using the osmosil, nanoparticles, silicons. So that kind of coating materials has properties under the surface waters, like superolympic conditions surface, but in the air, open air, it's super hydrophilic surface. So this is the main important part of the coating materials. And we would like to increase the productivity by 50% because of the less biofilm forming systems. And then we only utilize the water to clean the system. As you know, if you would like to cultivate different species, you have to clean up the reactors with some chemicals. And at the end of the day, you cannot utilize the water because of it is wastewater. It is polluted by the chemicals. So we would like to reduce the use of chemicals for cleaning reactors by 100%. And then at the end of the day, we decrease the water footprint for cultivation of microalgae. And this study aims to investigate the hormosil coating classes having anti-biofouling properties to overcome the biofilm attachments. So we use column reactors at the end of the projects, but now we tested the coating materials using the slides, glass slides, and for two different species, Chlorella vulgaris and Ettlia. And in near future, we will focus on also seawater species for this project. And the microalgal bioform structure and light penetration were determined after the 14 days of cultivations, and the biofilms on the coating classes were observed using the photometers. And to understand the biofilm structures on different coating classes, we utilized the fluorescent microscope to see the morphologic structure of the biofilms. And you can see that these figures, this is like coated slides, and this is without coating, non-coating materials. After 14 days, the non-coating slides almost covered by the biofilms. But we would like to also see the light penetrations, and the two coatings material has a potential for light penetration when we compare with the non-coating materials. So it's the first results when we tested. The overall, it is observed that the pieces and particles adhere to the non-coated surface firmly. This is the slice without coating, non-coating at the left sides, and it is the coating material with 10.4, and this is also coating material with 12.2. And when we look the microscope images, we can see small dots here, but the penetration is very high when we compare the others. So we tested for the Ettlia at the same time, and we observed the same coating material has a same potential as a anti-biofouling materials. So we focus on how can we increase the efficiency, especially the light penetration efficiency. So coating material is working now well, quite well, but it should be tested for different conditions. The next step we'll test with the outdoor cultivation systems, and not only slides, but also the all tubing reactor will be coated by the specific osmosil coating materials, and then we will test it first of all in the lab scale, and then we would like to test outdoor. So the process of adhesion on the coating was examined by the means of fluorescent microscope. We observed, according to the results, the 12.2 coating demonstrate the best light transmissions results for both microalgae species. Also, this project funded by TÜBİTAK. We would like to thank TÜBİTAK, and also we would like to thank to Professor Berat Haznedoroğlu for supplying us in terms of pre-cultures as well as his knowledge on technical and scientific cultivations during the projects. If you have any question marks in your mind, I would like to answer that. So this is a new topic for all of us. We would like to increase the efficiency during the cultivation. Yep. Yeah, it is the main actually drawback for the system. The coating material is very expensive at the moment. So if we know the really good nanoparticle species, silicon nanoparticle species, then we would like to work on the decreases of the cost. Now it's really expensive. Coating method designed by us because of I have two colleagues from Çanakkale 18 Mart University from from chemical engineering departments. They focused on only the surface coating materials. So we invented, we also developed by ourselves. Excellent. Thank you. You're welcome. Actually, at the moment, in the laboratory scale, 3 times we can use the same slides. There is no harmful effect on the surface, but we will see on the full-scale applications near future. Then I can clearly say that. But this is the main drawbacks as well, because of the sunlights and some circulation in the reactors effects on the surface structure. We would like to see how many times it can be useful for cultivation.
Do you also know the thickness of what's the thickness of the coating?
Actually, it's very, very large, 0.01 millimeters at the moment, but the main perfectness is the contact angle. So we try to reach the contact angle like 10 or less than 10 degree. So, please.
Very nice work, and of course much needed in the field. Can you tell me what was the main rationale when you designed your compound for coating? Was it really mainly the hydrophobicity properties, or did you think of any other physicochemical properties?
Actually, in the future, first of all, we tested the hydrophobic situations, and near future there are different kind of chemicals and superophobic under the waters as well. It will be tested, and maybe we will focus on the other physical properties of the coating material, maybe roughness or the flattening of the surface material, and it will be tested. It is like a pre-test of the first test setup also, first setup.
And this
Yes, actually we also changing the other, for instance, this is the freshwater results, but the seawater is more harmful, and we will test it. In that time, maybe we should change the other properties, yes, the other components, maybe.
If I may ask just one practical question, so how do you actually physically do it? You know, when the tubular parts of the bioreactor are ready, or do you kind of premix it and then
There's a specific, actually also we invented that material, like there is like a nozzle, 360 degree pressing of the coating materials and pass through the inside of the reactors. And then also the other method is deep coating method, but in that time it is really difficult because of we consume a lot coating material because of inside and outside coated if we use deep coating. So our aim to coating inside of the tubular reactor. So the special instrument was invented by us.
But as we heard today, the outside is also important because it is, has to be cleaned, right?
Yeah.
That's energy expenditure, isn't it?
Yeah.
So you really want to have it coated on both sides, I presume.
Maybe in that time we maybe use a like less expensive material for the outside. So this is maybe second step of the research or further step of the research. Yeah.
Very, very important work.
Yeah.
Thank you. Congratulations.
You're welcome.